Okay, we'll start the afternoon session by Simon Telen, Adjoints and Canonical Differential Forms.
Yes, thanks for the introduction and thanks to the organizers for having me. It's a great pleasure. All right, so this is about colorful pictures. I'll speak about two papers. The first one is entitled Adjoints and Canonical Forms of something called Polypols. This is a paper with many, many authors. So this actually came out of a study group that we had with all these people. And in the end, we decided to write some things down that we discovered during this, during this effort. And so the many authors maybe justify the large number of pages. This is a 68-page archive preprint. And in mathematics, that means that the review process takes 3 years. Okay, so this is published on the archive in 21. It's now accepted in Documenta Mathematica. And then at the very end, I'll speak about a paper with a similar title, Replace Polypols by Tree Amplituhedra. This is with Christian and Rainer, and it's accepted in Mathematica Scandinavica. Okay, so I'll start by talking about adjoints of simple polytopes. So P is a simple convex polytope in d-dimensional real projective space. So simple means that every vertex is contained in exactly d facets. And I'll make a slightly stronger assumption. I'd like the arrangement of hyperplanes that I get from the facet hyperplanes of P to be simple. So you can think in the language of this conference, this is a uniform matroid. So I'd like that none of these facet hyperplanes, so no d plus 1 of these facet hyperplanes meet. Okay. So the notation here, partial P means Euclidean boundary, and the bar means Zariski closure. So I just take the union of all facet hyperplanes. Okay. R of P denotes the residual arrangement. This consists of all the flats of this hyperplane arrangement which do not contain a face of P. So in the intersection poset of my hyperplanes, I look at all the linear spaces that do not contain a face. Okay, so here's some examples. If you take convex polytope and a line as a line segment, the hyperplane arrangement consists of 2 black dots, and the residual arrangement is empty because both dots contain a face of the polytope. Okay. Slightly more interesting, if you look at a quadrilateral, this green quadrilateral in the plane, then these 2 blue dots, they form the residual arrangement. So these are intersections of the boundary lines that are completely outside the polygon. And then you can imagine you have a 3D polytope that locally looks like this green thing. And now you see that this facet right here and this facet on the other side, they meet in a blue line, which belongs to the residual arrangement. So in general, you expect that the residual arrangement is something of codimension 2. Okay. I'm going to use this residual arrangement for the definition of the adjoint. So I'll say that a polynomial A, this is a homogeneous polynomial of degree k minus d minus 1. K is the number of facets, d is the dimension. This is called an adjoint polynomial of my polytope if it belongs to the vanishing ideal of the residual arrangement. Okay, so it turns out that the right degree to look in is k minus d minus 1. I say this is an adjoint polynomial if it vanishes on the blue stuff. And the variety of this adjoint polynomial is a hypersurface in RPD. It's called adjoint hypersurface, and it contains the residual arrangement. Okay, questions about this? Okay, so one reason why this is nice is it's unique. So you can speak about the adjoint hypersurface of a simple hyperplane matrix or a simple convex polytope. So this was proved by Kathleen Kohn and Christian Ranestad. My polytope P has a unique adjoint hypersurface. So the adjoint polynomial is uniquely defined up to scaling. Here's another example. This will serve as a running example throughout the talk. So if you draw a pentagon in the plane, this is in green. The hyperplane arrangement consists of the 5 lines defining the edges. The residual arrangement are the 5 blue points, and then there is a unique adjoint conic in red that interpolates this residual arrangement. So I denote this A sub P. Okay, so this is the adjoint canonically associated to this polytope. Good. So you can already see why such an adjoint could exist. So anytime you draw 5 points in the plane, there'll be a conic interpolating them, right? So then it's a theorem that if these 5 points come from a polytope, then there's a unique solution. Sorry. Yeah.
That degree is the smallest degree where such a A can exist.
Yes. That's right, and it exists uniquely. Something, okay. So maybe you're confused. So here I'm switching to affine notation. Okay, so I'm drawing you the picture in the affine plane. This is now a non-homogeneous polynomial in X and Y, but it's okay. It represents a conic in P2. Anything unclear? Otherwise, okay. So just to put this into context, these adjoints, they have been invented and reinvented a couple of times and in different contexts. So I just listed a very incomplete list of references here. So the first time I know of that these adjoints appeared in math literature is in a book by Wachspress called A Rational Finite Element Basis. So in figure 2.3 of that book, Wachspress drew a quadrilateral and the adjoint line. So the motivation for this book was Wachspress wanted to, he was interested in finite element methods for numerical PDE. And usually in that literature, people use meshes that consist of triangles or rectangles. And he wanted to generalize this to other polygons. So he wanted to make these methods more flexible so that your mesh can consist of arbitrary polygons. When you do this, you end up generalizing barycentric coordinates for the triangle. Okay, so that's what he is.
I think some people call them Wachspress coordinates or something like
Wachspress coordinates. They have been called Wachspress. Yeah, I think among other people, Kathleen and Christian call them Wachspress coordinates. And then Warren did this for polytopes in arbitrary dimensions. So he generalized these barycentric coordinates or Wachspress coordinates to convex polytopes of arbitrary dimension. This is a paper by Garcia Puente and Sotile. They were interested in geometric modeling. So they studied surface patches and ended up using adjoints in that setting. This is a 2020 paper by Kohn, Shapiro, and Sturmfels. They encountered adjoints in the context of statistics. So it turns out that the adjoint is a numerator of the moment generating function of the uniform distribution on the polytope. And then very recently, I discovered this paper by Paolo Aluffi, who started, I think, from an observation by Kathleen and Christian Ranestad that adjoints have something to do with the Segre classes of monomial subschemes of a smooth variety. And in this paper, he shows that under some assumptions, adjoints are dually Lorentzian. So they have something to do with Lorentzian polynomials if you make some assumptions on the polytope. And of course, the reason why we're here today, so that also the adjoints also show up in particle physics, but I'll have a couple of slides on that later.
Mm-hmm. Okay, so there are, under the moment map, they give a T invariant measure on variety.
Or maybe this is a question for Bent. So if you look at the generating function of the moments, where you consider the uniform distribution on, this is a rational function whose numerator is the adjoint of the polynomial, of the polytope. Yeah. Good, okay, so it turns out I'll have plenty of things to say about polygons. So you can say some interesting things about two-dimensional polytopes. From what I said earlier, you can deduce that the adjoint of a k-gon is a curve of degree k minus 3. This is k minus d minus 1, right? These two. Again, so how do you prove that an adjoint exists? Well, the residual arrangement consists of k choose 2 minus k points. That means all pairwise intersection of intersections of the edge lines minus the vertices. And the number of k minus 3 forms, k minus 3, a degree k minus 3 ternary forms is the same number plus 1. So you have just enough conditions to uniquely define, at least you can expect that you have just enough interpolation conditions to uniquely define the red curve in this picture. So now that we're still talking about real points, before we complexify everything, this is a statement about the real topology of the adjoint curve of a polygon. Okay, every time you see this long acronym, this is the group from the reading group. Right? The adjoint curve of a k-gon is hyperbolic with respect to any point in the polytope. So that means if I pick a point inside the orange octagon that you see here, then any line passing through it will meet the purple curve in the degree many real points, in this case 5 real points. Okay. And it has the maximal number of real nested ovals. That means you take k minus 3 over 2 and you round it down if it's not an integer. In this example, as I said, k is 8, so the orange region is an octagon. So there can be at most 2 nested ovals, and the rest is a pseudo-line. So if k is an even number, then k minus 3 will be an odd number, and you have some ovals and 1 pseudo-line. So the way you prove this is by learning, so you learn the sign of the adjoint on all the line segments that you see in this arrangement of lines in the plane. So you, for instance, here red means that the adjoint takes a positive sign, and blue means that the adjoint has to take a negative sign. And then you learn how many ovals there have to be, and you conclude that there have to be the maximal number of ovals.
Say the same thing, but like starting with the sentence that the polynomial AP is hyperbolic.
So can you say that? The adjoint polynomial is a hyperbolic polynomial with respect to a point, so the hyperbolicity cone contains the polytope. That's what I'm saying. So it's not hyperbolic with respect to any point. Right? Mm-hmm. Mm-hmm. Okay, so that's nice. So these adjoints, they are a nice source of hyperbolic plane curves. Some more examples. Our running example, you can see one glorious oval, right? And here, the heptagon is special. So I'll talk a little bit more about the heptagon later. So if k is 7, then the adjoint is a quartic in the plane, and it has 2 ovals, both containing the heptagon. Okay. So now I'm going to complexify the story. So I'm going to think of a k-gon now as a point in this space. So if I just write math BBP, that means complex projective space. So this is the complex projective plane dual. And I take k copies of it. And this represents a choice of a line in each of these, a line in P2 every time. Right? So a line in P2 makes an edge of the k-gon. And I mod out by the dihedral symmetry group. So this is the dihedral group dk. The adjoint map definition sends a complex k-gon in here to its adjoint polynomials. This is a rational map, which is well defined by a theorem I showed, which takes k-gon to its adjoint. So you can study the geometry of this map. So in particular, you can ask for which values of k would this be a generically finite map, or what do the fibers look like? What does the image look like? So if we want to study when this map could be generically finite, we can start by comparing the dimensions of domain and codomain, right? The only scenario in which this could be generically finite is when these dimensions agree. The dimension of the thing on the left is 2k. And the dimension on the thing of the right is this binomial coefficient. It turns out that these two things are equal if and only if k is 7. Okay, so the heptagon is special in this story. So the adjoint map alpha 7 is dominant and it's generically finite. It has degree at least 864, at least that's what we showed in 2021. So we did this using a certified numerical computation. And then Reiner with other co-authors, Agostini, Plauman, Sin, and Wesnig, this year published a paper in which they showed that the number is actually 864. And for this, they use intersection theory and something called the Scorza correspondence. So it's quite, I mean, it's not trivial, okay? But it's an interesting paper, and I just wanted to advertise it. Okay, so 864 is the number. Okay, so this equals 24 times 36, and in this paper you can read that there's actually 24 polygons for each of the 36 even theta characteristics of the quartic. It's pretty interesting. Okay. So I said this is a numerical computation, and using the computation that we set up, you can actually generate several heptagons with the same adjoint. So that's what happened in this picture. So here you see a green heptagon and a black heptagon, and they both have the same purple quartic adjoint. Okay, that's it for polygons. Good time for questions. If not, let's move on. So the paper had polypols in the title. So on this slide, I'll tell you what a polypol is. The data that defines a polypol with the adjective rational is as follows. So we fix k distinct rational plane curves, C1 through Ck, of degrees d1 through dk. Okay, so you could not require these curves to be rational, but it'll become clear later why I want to do this. If these curves are rational, we end up studying rational polypols. And between two consecutive curves, so I fix an intersection point that is called a vertex. Okay. So I require these to be transverse intersections in this definition. For the purpose of this talk, this is not what we do in the paper, but for today, I'm going to assume that the union of all these boundary curves has only nodal singularities. Okay, so what's the idea of this definition? We want to basically consider shapes in the plane that are the nonlinear analog to a polygon. So we want things that have boundaries that are nonlinear. So this sort of looks like a quadrilateral, but one of its boundaries is given by a leg of a hyperbola. I say this is a polypol of type 112. These are just the degrees of the boundary curves. This little orange triangle-like thing here is a type 222 polypol. Okay, and of course, yeah, you can guess what the purple things are. So now I'm going to define an adjoint for such a rational polypol. I'm going to say the residual arrangement is the singular points of the boundary curve minus all the things that I called vertices. Okay, so this is a complex definition. And a polynomial A of degree sum of the di minus 3 is adjoint to my polypol if it belongs to the ideal of this residual arrangement. And again, so if I take the variety of this polynomial, this is called adjoint curve of the polypol. As you can guess, so why do we set it up like this? So if you fit in with these conventions, my polypol has a unique adjoint curve. You can study the adjoint map like we did before. We could ask what kind of polypols. Okay, so the other way around. So in which scenario is the map that sends a polypol to its adjoint generically finite? And when you do this, by comparing dimension, it turns out that there's only 9 possibilities. So the number 9 is the case 1, 1, 1, 1, 1, 1, 1 with the heptagon, right? And the only other possibilities are shown on the slide. Okay, so otherwise this dimension comparison fails. These are cartoons. Okay, so this is of course it's not an algebraic curve, but this represents a quintic. A rational quintic has 6 nodes, right? Okay, so for instance, a polypol of type 2, 2, 2, 2 is something that's bounded by 4 conics. Turns out that among these 8, only 7 actually have a generically finite adjoint map. Again, this is shown with a certified numerical computation. And this one was kind of tricky because we thought that when we were computing this, and maybe something went wrong with the numerics, but then having a closer look at the Jacobian, etc., we thought that actually something more was going on. And turns out that indeed type 1, 3, 1, 3, even though the dimensions match, it is so that an adjoint to such a polypole has a positive dimensional set of polypols associated to it. Oh, that's this video, right? So here you should focus on this thing. This is a 1, 3, 1, 3 polypole. It's moving, but the red adjoint is fixed. So this is a one-dimensional family of 1, 3, 1, 3 polypoles with the same adjoint quintic. Okay, so if you like a challenge, we don't know what the number 864 is for any of these cases. So the polynomial system that we set up to compute these things, for instance, in this case, it is a system of 68 equations and 68 unknowns. And what we need to do is find one regular isolated solution. Right? And this you can sort of do by just choosing the polypole and computing the adjoint. But to compute all the points in the fiber, this is really challenging. So one thing is that there's a huge symmetry group. In this case, there's a group of order 700,000 something acting. So that means for every real point in the fiber, you get 700,000 points by symmetry. So this is really a hard system to solve. Okay. All right, that's it for adjoints. I'm slowly getting to the second part of my title, unless there's questions. Okay. So the second part of my title was canonical differential forms. I was gonna delete these slides because Chris yesterday introduced this beautifully, but I think this is one of these definitions that you maybe like to hear twice if you heard it for the first time yesterday. So I'll tell you again what a positive geometry is, according to this 2017 paper. I'm going to fix a d-dimensional complex irreducible projective variety. It's called X. And I want it to be defined over R. And inside of its real points, I pick a d-dimensional semi-algebraic subset. So in particular, I'm asking that this X has enough real points. As we've seen yesterday, the tuple X, X greater than or equals 0 is a positive geometry if it satisfies some axioms. But I was first going to show you some examples of positive geometries, I think most of which Chris also showed. So if you take the positive line, so R non-negative union infinity, this is a line segment inside the Riemann sphere. That's a positive geometry. More generally, if I take the positive quadrant in P2 non-negative, so this topologically looks like a triangle, that will be a positive geometry. More general convex polytopes are positive geometries. You can generalize this in a different way by looking at the intersection of the positive points in projective space with the Grassmannian. So GRKN non-negative is a positive geometry. Positive toric varieties are positive geometries. And one thing that that hasn't been discussed so far is that with the current definition, not all spectrahedra are positive geometries, which is something that might be slightly annoying if you are into real algebraic geometry and you like to think of spectrahedra as positive regions. So with the current definitions, these are not all allowed. Okay, so what's the definition? As Chris said, so we require that the interior of the non-negative part is an oriented manifold, such that if you close it up, you get X non-negative back. The algebraic boundary, which is defined as a Zariski closure of the complement of X greater than 0 in X non-negative, is a union of divisors in X. This is called partial A to emphasize that I'm talking about the algebraic boundary. I I define the non-negative part of the ith boundary to be the closure of the interior of the I intersected x non-negative. So again, think about the polytope, right? If you hear the divisors are just my hyperplanes from before. If I fix one of these divisors, I intersect with x non-negative, I get a line segment, and then I take the closure of its interior, I just get this line segment back. Okay. The definition says that x non-negative is a positive geometry if there exists a unique meromorphic D form called canonical form, such that it satisfies some recursive axioms. If x has positive dimension, then this form is required to have simple poles along each of the boundary divisors. And only there. There can be no other poles. This will be important. And if you take a residue along a boundary divisor, then you actually get the canonical form of the positive geometry defined on the boundary. Okay, so we saw yesterday. And if you're down to a point, then x itself is a point, its non-negative part equals x, and the canonical form is plus or minus 1, depending on the sometimes annoying orientation. Yeah. Okay, let's do some examples. I told you line segments are positive geometry, so here I consider the segment AB. Boundary divisors are D1 and D2. The claim is that this is a positive geometry inside the projective line. And I claim that the canonical form is b minus a over x minus a times b minus x dx. Whatever multiplies dx is sometimes called canonical function. So let's check that this is true. So for this, I need to take residues along the boundaries. So if I take this form and I want to calculate the residue along x equals a, then what you do is, well, you write this form as dx minus a over x minus a times something else. Okay, and then you evaluate something else at x equals a. That's how you compute a Poincare residue, and the output is 1. Okay, so this has residue 1. On the other boundary, so when x equals b, if you write our form this way, then a minus sign pops out. Okay, so this has opposite orientation, and here the residue is minus 1. Okay, so this satisfies all the axioms. Okay, back to our running example. So I claim that our green pentagon is a positive geometry in P2 with this canonical form. So let's parse it. In the denominator, we just have 5 linear equations. These are the 5 equations for the black lines, because we want poles along the boundary, simple poles along the boundary. And you can guess what the numerator is. So the numerator defines the red adjoint curve that we talked about earlier. Let's verify this at least on one boundary. So let's take a residue along the boundary with the easy equation, where x is equal to 0. According to, so that the convention I'm taking, which is also what Chris did yesterday, is I will write this as something times the x over x. For that, I have to switch the order of x and y. So a minus sign pops out. And then I have to set x to 0. That gives me this thing. So now I have a 1 form on this boundary x equals 0. And at first glance, this looks a bit problematic, because now this has 4 poles, while my line segment only has 2 boundary points. So I can only have poles along the boundary of this line segment. But fortunately, we fixed the numerator to be something that cancels these extra poles. So now you see that the numerator of this form is necessarily something that interpolates the residual arrangement. And that's how adjoints enter this story. Okay. Good. So the result is, so the spurious poles are canceled, and you end up with this thing, which is something like what we found for the line segment. So it's the correct thing on this side. Okay. Questions about this?
So this y is 1 and equals 3. These are the verses of the polygon, right?
That's right.
So why is the residual arrangement clearly important? Is it clear that?
Well, so this pole cannot be there, because that's this point, right? So we need to cancel it using the numerator. So I necessarily, whatever's in the numerator has to interpolate this residual arrangement. And yeah. Okay. And so here you also see that the numerator can only have, okay, I'll say more about that later. Good. So here's a theorem which I don't know, so I don't know who to attribute this to. So this says that a polytope in PD is a positive geometry with this canonical form. Chris said yesterday you can read about this in some nice lecture notes by Christian Gatz. That's certainly true. I'll later have a reference to some overview notes by Thomas in which he discusses this. Okay, so just to wrap up the story about these polypols. So it turns out if you take a rational polypol and you add some extra adjectives, right? So my story about polypols so far has been purely complex. So I need to add this adjective quasi-regular to make it look like something that looks like a polytope. Then this is a positive geometry with canonical form. It's adjoint divided by its boundary curve equations. This is an example I showed before. So here is the canonical form. In the denominator, you see x equals 0, y equals 0, and something quadratic equals 0. Okay, the adjoint is the purple line. That's the numerator. Okay, just to tell you, so the assumptions that I made on my rational polypol so far were a bit restrictive. So you can construct more general nonlinear shapes in the plane that are positive geometry. So it's certainly not true that the only positive geometries are the quasi-regular polypols. For instance, what I didn't allow is that you take only one curve. So you can take just one rational curve in the plane, like the ampersand curve, and choose one of these regions. Right? And it turns out this works too. So if you choose this region right here as your positive region, and you use this in the numerator, so you call this the adjoint line, this is a positive geometry, but it doesn't fall under my definition of polypol from before. This one, this orange thing is also a positive geometry in the plane. It doesn't fall under my definition because I didn't allow this, right? I wanted transverse intersections between my boundary curves. And if you think about it here, so because this is a singular point, my adjoint curve should not only vanish there, it should also have some tangent direction that we need to impose, right? So here we impose a interpolation condition and also some tangency conditions. So that's two conditions here, one condition here, and then there's two complex intersection points that we don't see, which make 5 conditions on the conic. And it's again uniquely defined. Okay, so these are examples which are not polypols, but they are positive geometries, and they have a unique adjoint curve in some sense. Okay. This is slightly different. So if I look at the intersection of two ellipses with 4 real intersection points, then this is not a polypol in the sense of what I explained before, because one curve makes up several pieces of the boundary. Right? That has not been allowed. Still, it is a positive geometry, but it does not have a unique adjoint. So in the sense that there are no residual points, and there is no unique line passing through no points. Okay, so but the numerator of the canonical form is this purple line, which is the line that you would obtain if you would pretend that this is just a quadrilateral. So this looks like a puffy quadrilateral, but now you just treat it as a normal quadrilateral, and then you get the unique solution, and that's determined by not by the interpolation condition, so by the condition on the location of the divisors, but that is fixed by the residue condition. So the residues being plus or minus 1 when you get down to the vertices. Okay. Questions about this? Yes. No, not off the top of my head, no. Can try to construct one. More questions? Yeah. Okay, I'm not sure I understood the question. Could you repeat? Yes.
So maybe not in this example, but in other example where this comes into work, your curve or the curve is expected the right number of degrees of freedom, the number of points to go through. But now we consider some more special configuration, not kind of a generic, we start to have special angles.
Yes, that happens. Yeah, but then the right thing to do is to take so for instance, you could start from, or you could be interested in computing an adjoint of something that's not a simple polytope, right? And then what you do is you take a limit of simple polytopes that goes to your non-generic polytope, and you keep track of the adjoint. That's the right object to consider in the canonical form. Yeah.
Is there space of, let's say, all quartic polynomials in the denominator that give rise to the same adjoint? So, for example, you could also have written two straight lines.
Yeah, that's very much computing the fiber of my adjoint map, right? That's exactly what that does. Yeah. Okay. Good. So there's a nice interpretation of this canonical function, at least for polytopes, in terms of dual volume. So this is sort of a bridge slide to the physics story. So let's look at this blue pentagon in the plane, and let's fix a gray point x in its interior. And what we do is we take this point x and we drag it to the origin. So we translate the polytope so that the gray point becomes the origin. This is now a polytope containing the origin in its interior, so it has a bounded dual polytope. So you can compute the polar dual of this polytope. This is denoted P minus X circ. And so if you've never seen this before, let me explain it this way. So the polar dual of this polytope is going to be a polytope whose vertices lie on the rays of the normal fan of this thing. And the position at which you put the vertex depends on how close the origin is to the corresponding edge. So if you would travel very close, if I would shift the polytope so that the origin gets very close to this edge, then the vertex here would sort of drift off to infinity. Okay, so you see that if you put your point near the boundary, then this becomes the dual gets an infinite volume. And it turns out that the canonical function measures the volume of this dual polytope. So adjoint divided by these linear forms with the correct normalization gives you precisely the volume of this thing. So you can see, so what I said earlier corresponds to, or amounts to saying, if you approach a facet hyperplane, this gets 0 and the volume explodes. And so what will be important for the next slide is that you can write this dual volume as a sum over the vertices. So the colorful simplices that you see here, they correspond to the colorful vertices here. So the color coding is that. So for instance, this orange vertex corresponds to this positive contribution to the volume. Okay, so how is this related to scattering amplitudes? I'm going to try to explain this in 2 slides. So I'm going to think of this blue pentagon from the previous slide as a Minkowski sum of 3 simpler polygons. This denotes Newton polytope of 1 plus x plus y, so standard simplex. This is Newton polytope of x plus y. So this is Q line segment, and this is a horizontal line segment. So if you sum these 3 things up, you get something that looks like my blue pentagon. And the Sij, these are called Mandelstam variables in physics. You can think of them as positive parameters for now. Okay, so every time you fix positive values for Sij, combinatorially, this polytope looks like this. These are the Lorentz invariants that Thomas talked about. So this is 2pi.pj.
Just a little comment, I think the comment that I made in Thomas' talk So this formula is basically dual of Brion's formula.
That's what, yeah, that's right. Thanks. Right, so you're talking about the summing over the vertices, right? Yes, I'm going to say that again. Mm-hmm. Right, yes. So, right, so here I labeled every vertex of this polygon with a triangulation of the pentagon. That's because I like to think of this pentagon as an embedding of the associahedron. This volume function, because my polytope depends on these parameters Sij, this volume function is now a rational function in x and y, but also in these Mandelstam invariants. And if you make one final substitution, so you set x minus S23 and y minus S34, then this magically equals the 5-point amplitude in the bi-adjoint scalar phi cube theory. That was also the topic in Thomas' talk. I don't know if Thomas, yeah. Right, so going to 6 particles instead of 5 particles, you'll be considering triangulations of the hexagon. So the amplitude will be turns out to be a sum over 14 things. These are the 14 triangulations of the hexagon. These are dual to the planar trivalent trees with 6 labeled leaves. So this is summing over graphs, and this is in the physics language, this is summing over Feynman diagrams. So this is maybe something you've heard as a slogan, that the amplitude is obtained as a sum over Feynman diagrams. And the way you associate a contribution to each of these Feynman diagrams, this is dictated by something called Feynman rules. Okay. So the 14 things that we're summing over here are the vertices of the 3-dimensional associahedron. And just to reiterate, so the 5 vertices of this thing and the 6 vertices of this thing correspond to the number of particles. The 5 vertices of this thing and the 14 terms in here, these are the numbers that Yara got excited about yesterday. Okay, these are the Catalan numbers that count the number of sums in this expansion. Okay. Final topic is Amplituhedra. So the Amplituhedron goes back to Arkani Hamid and Trinka in 2014. The data defining an Amplituhedron, we've heard this, is a matrix Z. So in my talk, this is going to be an n times 4 matrix. So there's n rows. Each of the rows is called Z1 through Zn, and I think of these as points in P3. So these are vectors with 4 coordinates, which are homogeneous coordinates of n points in P3. This is the notation Lara used earlier today. So this is the ijkl is the minor indexed by ijk and l. I require these minors to be positive. Okay, so this is a totally positive matrix. You can use this matrix in several ways to define a map. And one way to do this is to define a map from Pn-1 to P3, which sends x1 through xn to the corresponding linear combination of the points Zi. Okay. Now, if you restrict, so this is a rational map. Okay, you cannot always do this, but okay. Turns out if you restrict to the positive part of Pn-1, then this is actually everywhere defined. And taking this linear combination, since we're in projective space, you can now think of as taking a convex combination. And the Amplituhedron with indices n1, 3, according to standard conventions, is the image of this of the non-negative projective space under this map. Okay. Yeah.
The polytopes, is it? I mean, if that volume of the Wolfensohn, how is it related to the joint variety?
It's in so the adjoint is in the numerator of that volume function.
Is there an easy way to see why that
Easy, I wouldn't say, or you can prove it, but yes, we can talk about that later. Yeah. Okay. Right, so I was saying this particular amplituhedron is the image of Pn-1 non-negative under this map. And this is just a convex combination of n points in P3, so it's going to look like a polytope. Because of positivity of the matrix Z, that polytope is going to be cyclic. So that means the combinatorial type of this polytope is fixed. And I've drawn it here for n equals 9. It looks a bit like a hammock. So this is a three-dimensional polytope, and there's a cycle of edges, Z1, Z2, Z3, Z4, up all the way to 9 and back to 1. There's a cycle of edges that's going to play an important role later. Okay, so these are some familiar amplituhedra. Some amplituhedra are just cyclic polytopes. Okay. But of course, I want to look at more general amplituhedra. So one way to think of the cyclic polytope is as a generalization of the simplex. So if you fix a matrix Z that has size 4 times 4 and a positive determinant, then this determines a map from P3 non-negative into P3, whose image is just going to look like a simplex. This is just an isomorphism. So the image is just going to look exactly like P3 non-negative. Doing what we did in the previous slide means I make this green vector longer, and I add more rows to the matrix Z. Okay, the result of this is that the image will look like a cyclic polytope. A different way to generalize this is to add more rows to X. So in a way, so now I want to use Z to define a map from the Grassmannian G24 non-negative into G24. And what I do is I take a point in G24, I represent it as a 2 times 4 matrix, and I just multiply with Z. Okay, this brings me back in the Grassmannian. And what you see here is a cartoon. So the Grassmannian G24 as dimension 4, I can't draw it, but my cartoon represents, the green thing represents the Plucker quadric. And inside the Plucker quadric, we're going to have some semi-algebraic region, which is the image of this map. And it's actually going to be bounded by linear things, like the simplex, except now you have linear inequalities defined on the Grassmannian. Okay, so it's much like a polytope, but not quite. And what I want to do in this talk is I want to do these two generalizations both at the same time. So I'm going to consider a map from G2n non-negative into G24. So for this talk, all amplituhedra, we're going to sit inside G24. We take a 2 times n matrix, multiply with Z, and we get a semi-algebraic subset of the Plucker quadric that is defined by, that is cut out by linear inequalities in the Plucker embedding. Okay. So funnily, the amplituhedra, they have actually served as the main inspiration for defining the positive geometries that I discussed before. But as Chris also mentioned yesterday, it's actually been wide open whether these things actually satisfy the axioms. And when I emailed, so when we had finished this many-author paper about polypols, I had emailed it to Nima to advertise it. And the first thing he said was, it would be great if you could do this for amplituhedra. So this is what we tried to do then with Rainer and Christian. So to define an adjoint for the amplituhedron, we first need to identify the residual arrangement. So what is the right thing to interpolate? So in determining this, there's some work by Lukowski, Parisi, and Williams that was very helpful. So they proved a conjectural inequality description of the amplituhedron, which tells you, or from which you can then prove what the algebraic boundary is. Okay, so this was very helpful in proving that the right definition for the residual arrangement in this case is a union of one-dimensional Schubert varieties. Important or interesting observation here is that you don't expect this to be one-dimensional. Now we have a 4-dimensional thing. If this were a polytope, you'd expect the residual arrangement to have dimension 2. That's not what happens for the amplituhedron. So the residual arrangement is one-dimensional, and it's a union of Schubert varieties. they are depicted by these diagrams. So this right here represents the Schubert cell of lines which touch the line Z2, Z3. This is one of the lines in the cycle on the cyclic polytope. Lines which touch the line Z2, Z3 and are contained in the plane Z1, Z7, Z8. Okay. So that's a one-dimensional family of lines that actually makes a line in P5 contained in the Grassmannian. And you can choose all such configurations where the red tick is not adjacent to the green triangle. So there's n times n minus 4 choices for this thing. The second type of Schubert varieties that are in the residual arrangement are depicted by this, and these are just lines which meet the line Z2, Z3, Z5, Z6, and Z1, Z8. So these lines, if Z is generic enough, these lines have nothing to do with each other. So this will actually make a conic in P5. So a quadratic curve in P5 that's contained in the Grassmannian and in our residual arrangement. Okay. So here you can pick any configuration of non-adjacent edges. You can put 3 red ticks on non-adjacent edges. Number of choices is n choose 3 minus n times n minus 3. Okay. So what we proved with Reiner and Christian is that if Z is generic, and this means that there is no line meeting more than four of the lines in the cycle, then there exists a unique hypersurface of degree n minus 4, which interpolates this residual arrangement. So this is actually, so existence was actually argued in a paper by Arkania Hamid, Hodges, and Trinka. So what we had to do is show that this adjoint is unique, and once you've done this, there's only one candidate for a possible canonical form, and you need to check that this satisfies the recursive axioms, which is what we did. So corollary of this is that if Z is generic, then this particular family of amplituhedra, they all sit inside G24. They are positive geometries according to the 2017 definition. And as I said, so for general amplituhedra, this is open, as far as I know. Okay. All right, this is already the last slide. So here's some selected literature. This is the Amplituhedron paper from 2014 that I referred to before. This is the paper in which Nima, Andrew, and Yara, they argue existence of an adjoint. This is the positive geometries paper. This one right here, in this one right here, you can read about this embedded associahedron story and the biadjoint scalar phi cube theories. And if you like a short and nice introduction to positive geometries, I recommend this 2022 paper by Thomas Lamb. That's all. Thank you.
Questions?
So if you look at the polytopes, so polytopes are images on the moment map of correct. So they kind of shadows of some kind of high-dimensional objects. So amplituhedra is also image of a positive Grassmannian. So like in many of these cases, positive Grassmannian, there are some objects, possibly simple objects, or some kind of living upstairs. Somehow these canonical forms comes from some maybe simple objects from upstairs. Is it like always the case that you can kind of for positive Grassmannian, you can kind of see this as
there's always a free
shadow of a high-dimensional object.
So you're asking, is this always the case for every positive geometry?
Well, probably that's, I don't know if anybody proved it, but like, is there like some kind of general ideas about this, or
I'm not sure. Well, I mean, you can take unions of positive geometries and they'll still be positive geometries. So maybe that's, if you exclude that kind of thing. I think I'd be a little bit surprised. But it would be, I mean, this is certainly a nice way.
Interesting examples. That's interesting examples are kind of shadows of some images of high-dimensional objects.
Yes, and such nice maps in the case of the moment maps, for instance, it's known that the canonical form of the positive orthon pushes forward to the canonical form of the point. It's under the moment. Thanks.
So we know that the higher loop amplitudes are actually not positive geometries because the canonical form, the maximal codimension residues are just arbitrary.
Higher loop.
Yeah,
That's right. So I should say it's a general tree Amplituhedra. Sorry.
But at higher loops, we still have these adjoints. We have these interesting numerators. They are unique, so presumably there are some adjoints for them as well. Now, do you know how much you can go beyond positive geometries to also have these adjoint curves? Because this would be a first example to look at.
I don't know. I think so. Elia, maybe somewhere here. Yes. So Elia recently wrote a paper about one Amplituhedra. Is that right?
Yeah, specific case.
Yes, exactly. In which you also write that it's not a positive geometry in the usual sense, but maybe it's a weighted.
But the adjoint is unique.
Adjoint is unique. Okay. So I don't know apparently. Yes.
Right, so in the polytope case, as you move the z around, the combinatorial type does not change, subject to the positivity condition on the matrix. Do you actually know if this is true as m gets higher?
I don't know. I don't know if that's true. I think this is widely believed. So our assumption, our genericity assumption in the theorem makes sure that we can predict the intersection poset of the algebraic boundary. This we need to identify the right adjoint and so on. But we're not able to get rid of that assumption.
So there are some known cases of plastic geometries where the canonical form is easy, like for example for the positive Grassmannian or some other cases. Is your philosophy true for those cases as well? Like for the, let's say the positive Grassmannian, can you write down the unique adjoint and check that the numerator of the form is?
Well, so I guess for the positive Grassmannian, it's the Park-Taylor form, right? So there's the numerator is one. That's correct. At least for the positive portion, that's what it is.
KN.
No, I'm thinking about 2n. Okay, sorry.
What about KN?
Same in general. Okay, same in general. So no numerator. Anything that looks like a simplex is sort of boring adjoint.
Thomas calls them simplex-like.
Simplex-like positive geometries is the key word. So if it looks like it, yeah. So as a simplex doesn't have an adjoint because any flat will make a face, right?
So there are no residual writing for simplex.
That's right. Yeah, but also you need so that the degree of the numerator is fixed, right? So the canonical class in P2, for instance, is -3. But if you have a pentagon, you need 5 forms in the denominator, so the numerator can only be of degree 2. If you take a simplex, you're gonna need something of degree 0 in the numerator, morally.
Yeah, it's unclear why. I mean, for the Grassmannian, it's the residual set that seems interesting. Doesn't seem boring to me immediately. Take these consecutive minors, you intersect, you force some of them to be 0.
But I mean,
Like a numerator of 1.
Yeah, but the residual set is interesting.
But I think the residual set is empty.
Canonical form is 1 divided by, in the top you don't have anything. You have only a denominator that corresponds to faces, like these consecutive minors.
Let's talk later.
Sorry, one more question. Do you know, so in case the numerator is actually square of a polynomial, do you see any reason for that? Or why?
That's not fair. I asked you this at lunch. I don't know. This is really intriguing. I don't know.
That is true.
I wanted to phrase the question publicly.
Any more questions? If not, we'll head to Rubenstein Commons for tea and resume at 4 for Nick Early's last talk.